Welcome to today's webinar. Today we'll show you new features for cross-section modeling and design in Rsection. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Sonja von Bloor will be the presenter today. She's the main responsible person for the add-on aluminium design and the program Rsection, and she works also in the customer support team. You can ask questions when you click at the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Sonja. Sonja, it's your turn.
Thank you for the introduction. I would also like to extend a warm welcome to today's webinar. I would like to present several enhancements that significantly simplify the modeling and editing of cross-sections. First, I will demonstrate the new option for the manual definition of subpanels and highlight the benefits it offers. Next, I will cover the improved editing of elements and parts, which makes the modeling process more efficient. After that, I will introduce the new reinforcement features for concrete sections. Finally, I will show how layers can be used to organize and structure your cross-section models more clearly. To begin, I would like to introduce a feature that will be particularly useful for users working with thin-walled steel or aluminum cross-sections. Subpanels correspond to the CT elements defined in Eurocode 3 and Eurocode 9. They form the basis for cross-section classification and for determining effective cross-section properties. Until now, these subpanels were generated entirely automatically. Based on the cross-section geometry and the selected design standard, the support conditions were determined and the individual cross-section components were divided into subpanels accordingly. In most cases, this automatic generation provides very good results. However, there are special cross-section configurations and application scenarios where different subdivision may be preferred. To address such cases, Rsection now provides the option to define subpanels manually. In the base data, I will open this dialog, you will find the option manual definition of subpanels. Once this option is activated, the automatically generated subpanels can be modified manually or completely redefined. Let us consider an application example with two cold-formed C-sections arranged back to back and connected by screws. The screws are here on these positions. In Rsections, such screws are often modeled using so-called zero thickness elements. Since these elements have a thickness of 0, they do not affect the calculated cross-section properties. I will open such an element right now, and there you can see that a thickness of 0 millimeter is here defined for this element. At the same time, zero thickness elements are not considered as supports during the automatic generation of subpanels. As a result, a subpanel is now subdivided at the screw locations. This represents a conservative assumption. You can see here that this subpanel is not subdivided at the screw position here and here. In practice, however, it's often desirable to consider the screws as supports. This is now possible with the manual definition of subpanels. The subpanel can be subdivided specifically at the screw locations so that the restraining effect of the connection is taken into account. To do this, I first activate the option Enable Manual Input of Subpanels in the base data. The subpanels can then be edited. For the subpanel in the left web, I keep only the upper element and set the subpanel extension at the end to 0 millimeter. I then subdivide the area at the screw location and define the next two subpanels using the middle and lower elements, which I select directly using the pick functions. Here I do this via special objects, subpanels, new subpanel. Then I pick here the middle element. This subpanel should be restrained at both sides, and the subpanel extension should be on both sides 0 millimeter. Then I do this for the lower element, so I select this element. This is also restrained on both sides. Subpanel extension at the end is 3.2 millimeter. I repeat the same procedure for the right web. So I delete here the two elements, and then the subpanel extension to the end is 0 millimeter. And then I create a new subpanel for the middle element that's also restrained on both sides. And I create a new subpanel for the element at the bottom, restrained on both sides. And the subpanel extension is set again to 3.2 millimeter. Alternatively, the subdivision of the web subpanels can also be achieved through automatic generation. In this case, the screws are modeled not as zero thickness elements, but as regular elements with a thickness greater than 0. To demonstrate this, I first deactivate the manual definition of the subpanels in the base data. The subpanels are then regenerated automatically according to the code provisions. Next, I assign a thickness to the two zero thickness elements. Here I define a thickness of 3 millimeter. As you can see, the web subpanels are now automatically subdivided at the screw locations. At first glance, this appears to produce the desired result. However, this approach has several disadvantages. First, the screw elements now contribute to the calculation of the cross-section properties, even though they are intended only to represent the connection between the sections. Second, the design of the cold form cross-section is no longer possible because the cross-section becomes branched at this location. This is illustrated using an example in RFEM. The member on the left has a cross-section in which the screws are represented by zero thickness elements. In contrast, the member on the right has a cross-section in which the screws are modeled using standard elements. During the steel design, a message is displayed indicating that the cross-section cannot be designed. Opening the design details provides a more detailed explanation of the reason. The cross-section is not designable because it branches in the area of the bolted connection. For non-cold form cross-section, this type of modeling would generally be acceptable. For cold form sections, however, it's not a suitable solution. This is exactly where the manual definition of subpanels provides a clear advantage. The screws can remain modeled as zero thickness elements, while their restraining effect is still taken into account. At the same time, the cross-section properties remain unchanged and the design of the cold form cross-section remains possible. Next, I would focus on the editing of elements and parts. In Rsection, a thin-walled cross-section consists of elements and parts. Previously, when an element was modified, the corresponding part often has to be adjusted manually as well. Especially for more complex cross-sections, this could result in a considerable amount of additional work. The previous behavior can be demonstrated easily. To do this, I first deactivate the automatic regeneration during element modification option, which can be enabled and disabled from the general context menu. I will now change the thickness of an element as an example. For this, I open here the table element, and then I define here a different thickness, for example, 5 millimeter. As you can see, the corresponding part remains unchanged. As a result, the element now extends partially outside the part and the model becomes invalid, as you can see here on this red color. To correct this situation, the boundary lines of the part previously had to be edited manually. To address this workflow, the automatic regeneration during element modification option is now available. I will undo my step and then I will activate this option, automatic regeneration during element modification. If I now change the thickness, then the thickness or the geometry of the part will also be changed. This keeps the model consistent without requiring any manual rework. In addition, the functions for creating and deleting parts have been enhanced. Parts can now be created or removed specifically for selected elements. To demonstrate this, I first select the relevant elements and then start the command for deleting parts that you can find here. Delete parts under elements. The parts associated with the selected elements are removed immediately. These functions can also be started without making a selection beforehand. For example, if I launch the command for creating parts, this is here, this button, a dialog box appears that allows me to select the desired elements directly. These enhancements are particularly useful when modifying, correcting, or repairing more complex cross-section models. Next, I would like to present several new features related to concrete reinforcement. It's now possible to define curved stir-ups and circular stir-ups, as well as longitudinal reinforcement arranged along arcs and circles. In addition, the familiar editing functions such as move, copy, and mirror are now available for reinforcement objects as well. I would like to demonstrate these enhancements using a new cross-section as an example. For this, I create a new file. I name it example 2. And then I activate the concrete reinforcement and I specify a concrete cover of 50 millimeter. For the materials, I use concrete grade C37. And for the reinforcement steel, I create a new material. And here I use B500S. The cross-section that I want to use is an oval cross-section that I import from the cross-section library. This massive oval, and here I want to use the geometry height 500 millimeter and width 800 millimeter. I will start by defining the stir-up. Here I create a new stir-up, and 2 stir-up types are available, standard and circle. The circle type allows a circular stir-up to be created quickly and easily. For this example, however, I will use the standard type because the up-round cross-section contains both straight and curved regions. Next, I define the cover points of the stir-up. To create a closed stir-up, I simply select the starting point once again at the final point. So I first select here all cover points, and then I select the starting point 501 once again as the end point. The individual stirrup segments are then listed on the Segments tab, where they can be edited if required. For example, segment types can be changed from straight to arc, or the control point coordinates can be edited if required. For the stirrup, I use a diameter of 10 millimeter. So I define this, and then the stirrup will be created. In the next step, I define the longitudinal reinforcement in the curved region of the cross-section. For this purpose, I create a new bar, and I use here the definition type multi-arc. This option allows multiple reinforcement bars to be distributed evenly along a circular arc. First, I select the start and end point of the arc. I then specify a bar diameter of 25 millimeter, and I define 6 bars to be distributed uniformly along the arc. I click here on Apply and Next, and then the bars are created. Next, I define the longitudinal reinforcement in the straight region of the cross-section. For this, I use the definition type multi-variable. As before, I first select the start point and end point. The bar diameter is again 25 millimeter, and the bars are arranged with an axial spacing of 100 millimeter. I then create the remaining reinforcement using the editing functions. To do this, I select the existing reinforcement and use the rotate command. Here I activate this checkbox Create Copy, and I define a rotation angle of 180 degrees with the origin serving as the center of the rotation. This allows the reinforcement layout to be transferred quickly and efficiently to the opposite side of the cross-section. Especially for symmetric cross-sections, this can significantly reduce the amount of modeling effort required. For the final topic, I would like to introduce the new layer functionality. For this, I open here the third example. Layers are particularly useful when working with larger and more complex cross-section models. They allow objects to be grouped logically and managed together. This makes it possible to selectively show or hide certain parts of the model, protect them from unintended modifications, or edit them independently from other objects. Layers are managed through the Layer Manager that you can open via Guide Objects, Layer, go to Layer Manager. Here you can create new layers or delete existing ones. In addition, the visibility of each layer can be controlled individually. Layers that are not currently needed can be hidden, resulting in a cleaner and more focused view of the model. Layers can also be locked for editing. Objects assigned to a locked layer remains visible, but can no longer be modified accidentally. Another important concept is the current layer. A new created object is automatically assigned to the currently active layer. This makes it easy to maintain a well-structured model right from the beginning of the modeling process. The Assigned Objects column provides an overview of the objects associated with each layer. For example, if I click on the points, the point editing dialog opens. All points assigned to that layer are listed. You can see this here in the point number, and can be reviewed or edited together if required. Let us look at a practical example. First, I create 2 new layers. For this, I create a new layer, reinforcement. And another one, reinforcement dimensions. I assign the color blue to the reinforcement layer and the color red to the reinforcement dimensions layer. At the moment, all objects are located on the default base layer, as you can see here on the assigned objects. No objects are assigned to the new created layers. I would now like to move the reinforcement objects to the reinforcement layer. To do this, I select all objects that I want to move to the reinforcement layer, and then I select here this reinforcement layer. As you can see on the layer manager, now these objects are assigned to the layer reinforcement. I do the same steps with the dimensions, so I select here my dimensions and then I move them to the reinforcement dimensions layer. To make the layer assignment easier to verify, I can activate the layers display option here in the navigator under display. The objects are then displayed using their assigned layers colors. You can see this here. The reinforcement is shown in blue and the reinforcement dimensions are shown in red. One of the main advantages of layers becomes apparent when controlling visibility. For example, if I want to focus exclusively on the reinforcement and its dimensions, I simply keep the reinforcement and reinforcement dimension layers visible and hide all other layers. To do this, I deactivate here this icon visible from the default base layer, and you see now only the remaining reinforcement dimensions are shown here. This makes it much easier to organize and work with even high complex cross-section models. This concludes the overview of the latest enhancements in Rsection. We have covered the manual definition of subpanels, the improved editing of elements and parts, the extended concrete reinforcement capabilities, and the new layer functionality. Thank you very much for your attention. I will now hand over to Andreas.
Thank you, Sonja, for your presentation. At the end of the webinar, I have additional hints for you. For example, to our online courses, where is the RFEM 6 course. That's a course for beginners. Then the Eurocode 2 course for the concrete design, Eurocode 3 course for the steel design, the Eurocode 5 course for the timber design, the Eurocode 8 course for the earthquake design, and the AI masterclass course for the use of artificial intelligence. For more information and prices, just scan the QR codes or click at the links here. You can get an RFEM6 course or a Eurocode course when you submit your customer project. Just scan the QR code to submit your project or click at the link here. And after we published the customer projects, you will receive such a course. There are free online services on our website. There's, for example, the Dlubal community. You can ask questions there, and you will get answers from our support team or other community members. Whereas, for example, the GeoZone tool for the determination of wind, snow, and earthquake loads. You can determine cross-section properties, download 3D models. The trial versions of RFEM6, RStab 9, are wind-free or Rsection. You can get more information on our website, dlubal.com. You will find the recorded webinars there, the knowledge base articles. You can ask the AI assistant Mia 24/7. Just try it. Okay, that should be also all from my side. I thank you for your attention. Thank you, Sonja, for the presentation. I hope we meet each other in a future webinar. See you then. Bye-bye.